Awesome. Hey guys, good evening. Thanks for joining. I'm just going to give us a minute to see if there are a few more people joining. If you're here, please do drop me a hello in the chat. Hey Robin, hey Ari. Welcome. Today's chat is going to be about data structures and algorithms. Hello, hello. Totally fine, Ari. Hope I'm saying that right. Hey, Jesse. Hope you guys are having a great night. All right, we're just about to get started. Before we just jump into it, a little about myself. I am an instructor at App Academy here in the New York campus hybrid model. Before being here, I was a public school teacher for about 10 years. I taught math, and I made the switch last year. I went to App Academy, and I'm an instructor at App Academy. Super happy to do it. Really happy to do this kind of thing because I haven't done a presentation like this in quite a while, so I'm happy to be here. Glad to hear you're a fan. As we get started, guys, if you want to just drop, anything about yourself in the chat. Do you have experience with coding? Are you a beginner just thinking about learning? I'd be really interested to know more about, who's watching. Yep. Once a teacher, always a teacher. All right, so we're going to jump into, talking about what we're going to learn tonight, what we're going to talk about. So the title is Data Structures and Algorithms. In particular, we're going to talk about stacks, queues, and trees. We're going to learn exactly what those things are as we go through the presentation. Some things you can expect to walk away with tonight. Just an understanding of what is a data structure and what situations might we prefer a certain data structure? How do we use them? Nice, we got an AA alum. And we have a beginner trying to learn in the chat. That's awesome. Robin went to a front-end boot camp. Nice. All right. So as I said before, guys, data structures that we'll talk about tonight, you'll know what a stack, a queue, and a tree are. So you know what those three things are and the basic API of how to implement them. So when I mention API, all that is just how can we interact with stacks, queues, and trees? All right, it's just the rules of how they behave. All right. In addition to that, we're going to talk a little about algorithms. The two algorithms we're looking at tonight are called BFS and DFS. They're searching algorithms. We'll talk more about it. The B stands for breadth. So the breadth first search, BFS, and the D stands for depth. It'll be a depth first search, and we'll use those for searching trees. All right. Hey there, I see I'm cutting out a little. Let me know if that continues. I'll try and see if it gets better. All right. So those are really our main learning goals. Just going a little bit into the exact bullet points of what I'm going to talk about. First, abstract data types versus data structures. Those sound like the same thing, but they are different, and we'll go over why. Stacks, of course. Queues, of course. Trees. Algorithms and methods, and then the 2 types of searching. If we have time at the end, we might, hit a bonus that's not on the agenda, but we're trying to do this in an hour, so we'll see how that goes. All right, we're gonna jump right in. Please feel free to ask questions in the chat. I'm gonna be monitoring, looking back and forth a lot, and looking to just clarify anything, that's not clear. Today, you're gonna see some strategies, but no specific code. So we won't be writing in a language. We won't be, talking about syntax of writing, but we will see some pseudocode and talk about logic. All right, starting here. So abstract data types versus data structures. They do sound the same. Let's talk about why they are a little different. The first thing is an abstract data type. That's a set of properties and interactions. It's the rules of how something behaves. All right. So it's really like the blueprint. It doesn't really work yet, but I can tell you what I want. A data structure, that's the actual implementation of the concept. And that's me actually putting together the different pieces that are going to give me the functionality I want. Maybe one of the best examples I can give is an abstract data type being a vehicle. All right, let's see if we can get some chat participation. So name a vehicle. Let's see if we can get some folks to just drop a vehicle in chat. Or a type of vehicle. There are many types, but they all kind of meet the same set of rules. So one type of vehicle might be a motorcycle. And then another type of vehicle might be a minivan. So they both take people and they move them. That's what a vehicle is supposed to do. An airplane, thanks Jesse, an airplane is another type of vehicle. It takes people and it moves them. But they implement that moving in very different ways. A motorcycle just uses 2 wheels. An airplane has wings, it flies. An SUV has 4 wheels, it holds 8 people, but they're all vehicles. The abstract concept is the same. How they get the job done is slightly different. Awesome, I see more people. Thank you. I'm glad to see you guys here. Crossover, a train, a boat, right? And some of those vehicles will get a better job, get the job done better than others. Maybe you just need a motorcycle, maybe you need an airplane. Let's look at some other abstract data types. Let's get away from the vehicle analogy. We've been there for a while. Okay, so the first 3. These are the 3 you're going to see tonight: stacks, queues, and trees. These are sort of the ones that most people will start with. I'm going to name 3 others that we're not going to talk about tonight, but if you're curious, I would encourage you to look them up. Another abstract data type is a graph. A 5th one is a linked list. And the last one I have for you guys is a heap. So those 3 in black are not covered tonight, but they are 3 other abstract data types. Got it. All right, guys. Oops. So we're going to implement a to-do list. So this is an example of us making our own abstract data type. So a to-do list is going to be our very own ADT, and it must. I like to really get the chat involved. I like to get folks involved. Probably a byproduct of, teaching middle school for years. But I'm going to ask you guys again, if I were to give you a to-do list, what must it do? What are the basic functions of a to-do list? Doesn't have to be too technical. Boom, let you put tasks on it. That's the core functionality. If I said, hey, build me a to-do list, it would have to be able to do that. So some other things to think of. It should contain an ordered list of to-do items. A lot of times a to-do list has to go in order. Do this, 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 this. So for our implementation, it must be in order. Keep track of the items that are done or not done. Track my errands. Provide tasks and complete them. Awesome. So you need to be able to read any item on the list. So you need to read the first item, the middle item, the last item. You want to be able to read those things. And then, yeah, users should be able to add items to the end of the list. So the list can get longer. So my question then is, well, I know we have some, different level of experience, some beginning coders, some mid-level coders. What data structure are we going to use to implement a to-do list? Knowing that we need to have an ordered list of items, we need to read any item on that list, and we need to be able to put new things at the end. I like the idea for checkboxes, but it's a little, is going to add more complication to something very simple for us. So if we're going to store all of these items and we want to keep them in order and read them later, we're going to use the humble array. So you might have heard of an array before. Think of an array just as a collection of slots. So starting at the first item, slot, 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 we number them starting at 0. Remember, when we're doing indexing in coding, we always start with the first thing being 0. Then the next item is 1, 2, and so on. Each slot is going to represent a task of our to-do list. So in order to get this done, we would use an array. That's an example of how an abstract concept can be implemented with something that already exists and that is concrete and already provided to us by most programming languages. Oh, there we go. I see a few people in there too. Chris said queues. Robin said an array. Absolutely. All right. So away from the to-do list, we're going to take a look at our first official ADT, the stack. All right. So some things to know about a stack. A stack is also a sequential collection of objects. It needs to be ordered. Not every data type cares about order, but stacks certainly do. All right. Stacks are known as last in, first out data types. We'll see a little more of that as we go. But the last thing that you put in a stack is the first thing that you can take out. You cannot take out something else, only the last item. All right. Users can add, or users can only add and remove items from the top of the stack. And users can always see what's on top of the stack. They might not be able to see what's in the middle or at the bottom of the stack. I would encourage you to think of this as a stack of plates. If you were to stack up 10 plates, getting that bottom plate is going to be really hard, basically impossible. You have to take the plates from the top of the stack. And that's how we expect stacks to behave when we're coding. Let's look at a visual demo. So the first thing we're going to see, one bullet point at a time, we're going to place 5 items on the stack. So what that looks like is this. 1, 2, 3, 4, 5. Notice the 1 came and dropped in, 2, 3, 4, 5 was the last thing that we put on the stack. Just like that stack of plates, we no longer have access to the number 1. The bottom of the stack is closed. When we remove an item, it's going to be the top. So we just removed 1 item and then we removed a second item. Generally, you can't remove 2 items at once. So notice those 2 items are being removed 1 at a time. You can't just take a chunk of the stack and lift it off, generally. And then if we put a new item, it's going to go right on top. Now that the number 6 is on top, we no longer have access to 3, 2, or 1 without removing the 6. That's the basic idea of how a stack is going to work. Okay. Not seeing any questions, and I'm going to continue to move forward. All right, so under our definition, a stack should have these methods. So in computer programming, methods or functions are just things that a stack should do, things that your data type is going to be able to do. And we'll give them common names. First, we often see push. Push is defined in many languages, not all, but many. Just putting something on top of the stack. We're pushing an element onto the stack, we would say. Next, we have pop. We can pop an element right off the top of the stack. It is no longer on the stack. In addition to removing it, we are also returning it. We'll talk more about returning things in just a sec. That just means once I remove the item, I need to present it to the user, whoever that coder is who wants that item. Next up, we have peek. So you should be able to see the top of the stack and not remove it. So you just want to look at it. Peek. Then the size. How many plates or how many objects are on the stack? The stack level, we can call that. How large is the stack level? And last but not least, empty. Just wanting to know if it's empty or not. Is there anything on the stack? We might want to know. So those 5 things are the functionality, the basic functionality that we are going to have in our stack. Next up, we're going to look at some pseudocode. So if you're interested to see some code, again, this is not a specific language. This is pseudocode. It just gets the idea across, and you can implement it in a language of your choice. First thing first, our stack, we're going to call it a class. For an object-oriented programming, when we define an abstract data type, we'll often use a class and give it the name that we want. So this class is stack. All right. In most programming languages, you'll have some sort of constructor. That just means, hey, when I started this stack, when I get a brand new stack, what should it look like? What should it do? And for our purposes, that's just an empty array. We'll call it the underlying array. All right, we know that an array is just a list of items. It's just a bunch of buckets, and we can put items in those buckets. Our next method here, function push item. This is when we're pushing things onto the underlying array. Remember, pushing just means put a new item at the end, or we can call it on top of the stack. All right. And then next up, we have pop. Pop's a little bit different. It's going to pop that item. We call it the top item. We're giving it a name. And then after that item has been removed, aka popped, we can return it. Whoever is popping an item off this stack, they might want to look at that top item. So we're going to return it to them. And that's the use of the return keyword, also very popular in a lot of languages. All right. We got a couple more to go. Okay. The constructor didn't change. Let's look at next, peek. So we want to peek. Remember, peeking is important. We want to look at the top without removing it. Removing it could break something. Or maybe we don't want to spend the time removing it. Our computers have great processors, but everything they do takes time, and we don't want to waste time, usually. So here's an example of how we're going to index. Remember, an array can tell you at index 0 or index 1, whichever bucket something is in, you can just pull that thing out and look at it without removing it. So let's not say pull out. You can just look at it. Right? In this case, we're using the word top to stand for, hey, whatever the last thing is. Depending on what language you're using, that'll have different behavior. But we just want to get the last item or the top item. And we return it. We're returning a reference to it. The user can look at it, but it was never removed from the stack. Last but not least, we got a little if else. Again, if you're getting into coding, you're going to see if else a lot. if the underlying array has a length of 0. That's what we're reading. If the length is equal to 0, that means it's empty. There's nothing on it. So we're going to say true. Empty is true. But if it's not 0, that means there has to be 1 or 2 things on it. There has to be something on it. So it's not empty, and we return false. And those are the functions that we're going to be defining for a stack, for a basic stack. All right. I'm hoping the pseudocode makes sense to you guys. Let me know if it does make sense. And if you have questions, don't hesitate to ask. Okay. All right. And that's it for stacks. So again, just to go back, before I move on to queues, I want to just pause and say, are there questions about the stack? Here are the methods that we looked at. Awesome, I'm glad it makes sense. All right, so if there's no questions, I'll try to come back if something pops up. Maybe it's lagging, but I will just move forward. All right, let's go forward. Boom. All right, the queues are up next. Queues, very similar to stacks. So let's take a look really quickly. A queue is a sequential collection of objects, just like a stack. The order matters. For those who might not know already, a queue is like a line. It is a line. You know, I'm from New York. We just talk about lines. But if you're over in UK, they'll say you're standing in a queue. It's just a line of people. It behaves just like that, a line of items. So the difference from a stack is that it is first in, first out. If you are entering a queue first, you expect to get out first. You don't expect to wait for anyone who entered after you. You get to leave first. All right. So users can only remove items from the front of the queue. And they can only add items to the back of the queue. You cannot skip in line. You cannot say, hey, put this thing in the middle of the queue. That's not how queues behave. All right. Of course, this is all very abstract. So we need to make it work. That's the job of a software engineer, make it work. So let's jump right into how that happens. Well, first of all, let's do a visual demo. Some lingo that you should know. The first bullet point, to on queue or end queue, on queue 5 items. All that's saying is put 5 items on the queue. The next bullet points both say to dequeue items. When you dequeue an item is leaving the front of the queue. And then we're going to on queue a new item. Let's see what that looks like. 1, 2, 3, 4, 5. They're standing in line. There are 5 items in the queue. We can insert them one after another. Here's where a queue is a little different from a stack. We can dequeue the first item, but then something else has to happen. We can't just leave the queue alone. In most implementations, you're going to have to dequeue that first item and move the rest of the items forward. Now 2 is at the front of the queue. And it's ready to be dequeued. And then we can move the queue forward again. Last but not least, when we add a new item, of course, it just goes to the back of the queue. It works exactly how you would expect it to. We need to write the code to do that, though, so let's take a look. All right, so here's the example API. Here's what we expect a queue to do under our definition. We need to onqueue, and we need to dequeue. So adding an item to the back of the queue and removing an item from the front. We need to have that functionality. It might also be nice to show the queue. So we're going to have a show method, and it allows us to look at the queue. We can look at who's first, second, third, and so on. We can look at the whole thing. But we're not going to return that to the user. We're just going to show it to them. And we'll talk more about how we're just going to show it without ever giving it to them. Always remember, don't trust the user. If you give them something, they are going to break it. If you want to show it, just show it. So, oh, I see a question here, and I'm going to answer that in just a sec. That's a good question. All right. The last thing we need, folks, we need to know the size of the queue, how many people are waiting in line. And we need to know if the queue is empty or not. These are just standard functions that most data structures should have. It's just very useful for the developers who use our work. So that's what we're going to look at. Now, just getting to this question really quick. When we take something off the queue, David says, do the indexes of each item get updated? And the answer is yes. So if we just go back really quick, remember, in coding, the first element is at index 0. So it's not super intuitive when you first start. But the number 1 here is at index 0. When we remove it and everything moves forward, now the 2 is at index 0. When we remove the 2, now the 3 is at index 0. And so you can imagine everyone moves forward 1 index. Really great question. And that's one of the things that makes queues a lot different than stacks. Stacks, it never changes. When you remove something, it doesn't change the rest of the things on the stack. All right. Let's look at some quick pseudocode. How are we going to do these things in code? Here are some examples. It starts off just the same. All right. So just like a stack, a queue can be represented with an array. So why not start with the very humble array? It's used in so many things. It does not get credit. It starts empty here. We need to queue an item, not any different than a stack. Once again, we just push an item on. That means put something at the back of the array. And then dequeue. So this is a little different. And in our pseudocoding language, I'll explain what we're doing. The top item, we're going to say underlying array dot pop, and we want to pop the element that is at index 0. All right. Now, your coding language of choice may or may not be able to do that. But in my imaginary pseudocode, I can do that. Pop off the 0 element, give it back to the user, and then everyone else will move forward in the queue. Okay. Let's look at some other things. All right. Show. So we want to show, again, we want to show the queue to the user, but we don't want to give it to them. Here's an example of how we might do that. So here we're going to print the queue. We're going to print it out. The user can see it, but we never give it to them. The reason being, if I just give you this array, remember the underlying array, it's not a queue. A queue is an abstract concept. So if I give the underlying array to the user, they might take somebody out of the middle, or they might have somebody skip the line. They might break the rules of how this queue is supposed to work, and that could break our entire program. So we don't give that power to them. Don't trust the users. Or have really good error handling, check for errors. All right, and last but not least, the size. So that's just, hey, give back the user, check the length of the array, and give that to the user. So we're not giving them anything special. They can't break anything. I'm just going to say, hey, there's 5 items, or there's 3 items. Nothing to break. I can return that right to the user. That's awesome. All right. Empty is the same way. We're not going to look at empty again. It's the same thing. All right. So that's the entire rundown for queues. Again, I'm going to give just a couple of seconds. Maybe you have a lingering question you want to jump in with, or you want to maybe take a look at my great animations again. Who knows? We're going to move on in just a sec. All right. Okay, guys. So next up, the main attraction. So stacks and queues, they're kind of like siblings. They're very similar. We can just use an array. It seems pretty simple. Now we get to talk about a tree. A tree, it's the next level. It's the next step. It's the thing you want to know after you learn stacks and queues. So let's just learn about it. A tree looks like this. All right, you might think of a family tree, right? And it branches and it goes down. This is just a tree of numbers. Let's talk about the parts of it. All right, it's a branching collection of nodes. We'll talk more about what a node is, but I think the idea of branching is pretty natural for folks to understand. Every node can have one parent. So again, going back to the idea of family trees, right? The parents generally go up high on that tree, and as you come down, it's their children. Every node can have many children. They can only have one parent, so it's not like a family tree. You can only have one parent, not two. The topmost parent, very special. Let's play that again for effect. Look at that topmost parent. It's called the root. The root is the topmost node. It has no parents of its own. For that reason, it is special. Every other node is a child of one of its children, or an ancestor, or a descendant, I guess we can call it. Except at the bottom, we also have some special nodes. We call them the leaves. If this is a tree, those are the leaves. They don't have children. They are the ends of the branches. The ends of the branches we call leaves. Take the terminology while it's easy. All right. Let's learn a little bit more about this particular tree and how we can interact with it. All right. So similar to how we made a class for stacks and queues, we're asking the question right now, do we need a tree class? Trees are a little different. They're funky. It's not like I can just line them up. They don't go in order. And the answer is no. The nodes do all the work. So each little node that has a parent and it has a child, maybe, they're doing the work. And I'll explain why. I'm going to pause for this great question. Would it be wrong to think of a tree similarly to a file system? And I can do that. I can put things on the screen. Your file system is a type of tree. So the directories starting at your root directory, right? Then you have several folders that have things, and those folders have folders. That is absolutely a tree. Your file system is a tree. Really great question. All right. So going back to talking about why nodes are more important than trees, or maybe, they're the same thing. We'll see. The connections between the nodes are really what form the tree. So those lines that you see connecting them, that's really what makes the picture of a tree. That's what a tree really is. All right. The nodes are the important part. The nodes store the values, and they connect to their own children. All right. The root is special because we can start at the root, and going down in some direction, going down, we'll be able to find other nodes. Essentially, folks, the root node is the tree. I want to harp on that just a little bit. The root node is the tree. And what we mean when we say that, again, going to our nice part here, the root at the top of that tree, if I said, hey, find another node, there's always a route down to another node. In many trees, many tree nodes, they will not be able to access their parent. Sort of it's a tricky data structure. Some of them do access their parents, but on our basic tree that we're using today, children cannot see their parents. So the root is very important. The root can see everybody. All right, let's jump into, again, using the root node as the tree. Let's look at a tree node and talk about how it's coded out. It's pretty short compared to stacks and queues, actually, because all you need is a constructor. So in this case, for our tree that we're about to look at, every node has a value. The value could be a number. Our tree contains numbers. It also has children, which are just other nodes. The only thing we need for a functioning tree or functioning tree node, it needs to be able to return its children. So if I say, hey, tree node, do you have children? It should return to me all of its children. Or it can return nothing if it has no children. It also needs to be able to tell me its value. So if I'm looking at a node, it would be useless if I didn't know what was inside. So I can say, hey, node, what number do you contain? And that node will tell me what number it contains. That is all that a tree node is going to be for our purposes. That's everything we'll need. All right. So far, so good. Okay, now let's talk about the real computer science, the real stuff. Tree searching algorithms. We got this big old jumble of nodes. Unlike a nice array, it's not in order. Unlike some other data structures, there's no rhyme, there's no reason. We just have 10 at the very top, and we have some numbers below it. And maybe we want to look for something. For example, what if we want to know, hey, is the number 90 in this tree? Very similar to a stack. In a stack, you can only see that top element. In terms of this tree, we can only see the root. I'm giving you the root, which is the number 10 in this case. That node that contains 10 is the root. You don't know if the number 90 is in there. Your human brain can look at this and figure it out, but a computer has no idea. So we use algorithms to figure it out. Algorithms are important because they're general approaches. What we're going to talk about right now can be used on any tree as long as it follows the rules of what a tree is. And we established those earlier. If you, maybe you don't remember, just let me know. But as long as it's a tree, these algorithms will work. All right, the first algorithm is called the breadth first search. That keyword breadth, that is just how wide something is, or going across the breadth of something is going across its width. So not going up or down, but going left to right first. In the case of a tree, we want to go across the tree, not down the tree. A depth first search is just the opposite. It doesn't want to go across the tree. It wants to go right on down to those leaves and look at the leaves first. And it will prioritize that behavior. And we'll see that happen in our demo. All right, let's take a look. The first one up is actually the depth first search. So let's take a look at that. We're searching for the number 90. Take a look, see if you can use your human brain computer to find the number 90. It's very easy. It's right there, right? So the number 90 is right there. If we're going to look for it, though, we need to do it programmatically. We need to do it in a way the computer understands. The computer can't just look at this picture. Well, depending. ChatGPT. So we need to do something. So starting at the node or the root, we need to check, hey, is this 90? Of course, that's the first thing to check. If it is 90, if it's 90, you are successful. You found 90. You can return that to the user. Maybe there's some information. You can tell them, yes, 90 is right here, or something like that. If not, so if you are not 90, then I need to look at your children. Maybe one of your children are the number 90. So are there any children that we haven't checked? We'll see this visually in just a sec, so please do bear with me. We're going to check the next child. And here's what we call a recursive search. Recursion is just when, as we are doing a depth first search starting at the number 10, we will also perform a depth first search on all of its children. I will show that visual in just a sec. In the case that you don't have children, or maybe you checked all of your children, go back up the stack, and we're going to see exactly what that looks like in just a sec. So let's actually do this. The steps are on the screen, so let's talk it out. Starting at the root, always starting with the root because that's all you're given. We're checking to see, hey, is this 90? No, it's not. That's why it's red. It is not 90. In that case, check your children. So we're going to look at the next child. Hey, this is the next child. It's 77. We're going to perform a DFS, a depth first search on 77 now. What that means is we're going to check to see, is it 90? And it's not. We're now back at the top of our instructions list. And since it's not 90, we're not just going to jump over to the 90. I know it's so tempting as a human. You think, hey, the 90 is right there. It's the next child. Move over. But no, a depth first search is going to go down to the bottom. It's going to check the next child, which is 88. So we are still not finding what we want. What's going to happen next? Our computer's going to crash. We got to 88. There's no way out. We can go down the tree. We can't necessarily go up the tree. That's not how most trees work. Any idea of what would happen next? I'm just going to give a 10-second wait time, see if someone drops an idea. And the key word there is stack. We're going to see how this is related to stacks. All right, we might not have ideas just yet. So, to reiterate, this is a stack. The first thing we checked was 10. And we put something on top of it. We are now going to the next thing, 77. 10 was on the stack. Now 77 is on the stack, and it's on top of the 10. And then we went to 88. 88 is also on the stack now. It doesn't have children, and we must do something. We can't simply jump over to the 98. What we can do is remove 88 from the stack, and then we'll check the 98. So again, let's look at that. We're removing 88 from the top of the stack and adding a new child to the top of the stack. It is still not a 90. Thank you, Brian. Absolutely. So we went to the next child, but only after removing that child from the stack. Pop the stack and insert the next. Thank you. Exactly. So now we're at 98. It's still not the right thing. Since we're doing depth first, we are going to go down further. 76, still not the right number. As you might have guessed, since 76 has no children, it is removed from the stack. And then we check the number 20. Still not the target. Now here's the special thing. 20 has no children. It is removed from the stack. 98 has checked all of its children. It is removed from the stack. And 77 has checked all of its children. It is removed from the stack. We have gone as far as we can for the child 77. We're back at the number 10. The number 10 has more children. It's going to check its next child. And it just so happens on line number 1, check the node value. Is it 90? We have finally reached success. After many steps, we have found the number that we want. You can imagine if the number was, I don't know, 39, which is another number way down here in the stat, way down here in the tree. We'll keep searching, and we're going to find that 39 eventually. We can find anything that's actually in the tree. If it's not in the tree, then we can't find it. Clearly, right? Awesome. Oh, I'm just realizing now. There we go. Probably want to make that picture bigger. All right. Next up, we're going to look at the breadth first search. This one's going to be a little bit different. Instead of talking about stack, 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 I'll be talking more about queues. Let's look at how that works. So, same idea. When you look at a node, is it 90 is the first question. If so, you're successful. You have found it. If not, then you need to queue up the children. That'll look a little different. That's different than just using a stack. And we'll see how that works. Do you have children? That is a typo. I'm sorry, guys. We're going to check the next child. That shouldn't say DFS, but we'll see in the visual right now. No matter how many times you read it, it happens. Teachers know. So we're going to BFS each time. And what that looks like is, here we go. Starting with the number 10, we're going to say, oh, the number 10 is not 90. So instead of just checking 77 and then checking children, we're going to look at all the children and queue them up. I'm going to play that again for effect. Notice how they are bubbling up in order. 77, 90, 35, 19. That is the order that I'm going to be checking these things because it is a queue. Whoever's first comes first. 77 gets checked. 77 is not the right number. And let's play this again for effect. Because it's not the right number, we are adding its children to the queue. So anything in a black ring right now is waiting on the queue, waiting to be checked. We're not going to check those children. They're last. The next thing on the queue is actually the number 90, which is awesome. We have now reached the number 90 in essentially fewer steps than it would have taken for the DFS version. All right. So that begs the question, is BFS better than DFS, and why? And we're doing pretty good on time. And so I'm interested to know what folks might say, if they have questions or if they have an opinion. So considering how much faster that is it better? If you've ever gone to school, you probably know it's a trick question, right? It looks like it's better, right? Yeah, sure. It has fewer steps. We just displayed that. We just showed that in a DFS, we had all these steps. Look at me going down the tree, many steps, and I finally make it to 90. Whereas in a BFS, it's pretty quick. It just, I mean, there were check 10, QQQ, check QQ, and then I'm there. Seems a little faster. Awesome. So I see, could you use both at once? Wouldn't which is better depend on the context? All right, you've hit the nail right on the head. It does depend. To the question of can we use both at once? We can't really use both at once. What's happening under the hood when you're running something like a BFS or a DFS, I guess if you have multiple like cores, you know, like a lot of computers now have quad cores or 6 or 8 cores. Every core can do one thing. So generally, when we're running a language, we'll just be doing one or the other, and we can't do both concurrently without some special tweaking. Yep, I guess it depends where we find the result. So just to showcase that, yes, wouldn't it depend on the context? Let's look at that. So as usual, folks, it always depends. You're going to find some things that work and they solve the problem right away. There's no magic. There's no magic data structure that does everything and does it all well. And no magic algorithm that does everything and does it all well. They both have their worst cases. So the worst case is like, well, this is the worst possible thing you could give me, and it took me a really long time to find it. So let's talk about that. In the case of a breadth first search, which we'll check first, we're going to search for the number 20. If you don't know where the number 20 is, take a moment, use your human brain computer, scan, and find the number 20. You probably found it by now because you're much faster at this, because you can look at the picture. But here's how our BFS works. Oh, excuse me, I went far. So we're going to BFS this thing. So going just line by line, we're going to check 10. Since 10 is not the right thing, we queued up all of its children. We're going to check those children in order. All right, let's check those children. Every time a child is not the target, we add its children to the queue. So everything that's in black is on the queue. Let's just look at that one more time. Notice the order that they're being added in. I'm going to check them in that exact same order. 88, 98, okay. I still have not found the 20. I checked the last children on the queue, and the last thing is 20. That is the worst possible thing that could happen for a BFS. You don't always know as the developer. Sometimes you just have to predict which one will be better. There's not always a way to know, but this was not a good one for BFS. Let's take a look at DFS really quick. If we're DFSing for 20, it'll look a little something like this. All right, so we've seen this before. We check 10, then 77, then 88. Before we can move forward, 88 gets moved from the stack, and then we go down. That's removed from the stack, and we have finally hit the 20. And that was a lot faster than the BFS, clearly. So we've just sort of proven there that it does depend. And so my question for you guys, I love turning questions back to the audience. It is what we are trained to do as teachers. What is the worst case target for a DFS in this tree? Drop that in chat if you have an idea. Drop that in chat if you're guessing. Doesn't matter. What do you think? I know it takes a couple seconds to pop up, so I'm just going to keep on talking about trees until I see some things. All right, I see Brian in there with a 72. I see David in there with the number 19. All right, so I noticed that folks are picking things that are down at the bottom of the tree here. 19 is duplicated, very tricky. Thank you for paying attention to detail. I kind of missed that one myself when I first looked at it. So if we are depth first searching, we're going to hit 19 right there. Oh, wait, you guys can't see my mouse. Silly me. Yeah, so we'll be hitting the 19. Let's see, what can we do? But 72 is the correct answer. 72 is at the bottom right of the tree. Since we're going down to each leaf one at a time, it's going to take quite a while to get over to that 72, and it is the worst case answer. All right. So just to wrap some things up, guys, we are coming up on the hour. We do have a bonus, and I think we can take a look at our bonus. I find it interesting. Here we go. Just from the top here. Abstract data types are blueprints for storing and accessing data. We can build ADTs using simpler structures. So today we used an array to stand for a stack or a queue. We add our own rules How can you interact with that array? That's what makes something a stack or a queue. It's all about the rules that you have to follow. All right. Now, what's important about stacks and queues is that they have to store data in order. And not every data structure is guaranteed to do that. So you have to be mindful that things need to stay in order. All right. And then lastly, trees, they don't store things in order. In general, my children can be a number that's larger or smaller. Trees by themselves do not regulate that. We can use the depth first search or the breadth first search algorithms to search a tree. We don't have to know the shape of the tree. We don't have to know how many children or how far down it goes. We can just use those algorithms. It's just that sometimes one is faster and one is slower. All right, folks. So that's the main portion. That's stacks, queues, and trees. If you'd like to stick around for a couple of minutes and take a look at a bonus, we're going to go to that right now. And if you don't mind, just dropping what you thought of the presentation down in the chat as we look at the bonus. Just some feedback for me, really valuable. I'd really appreciate that. So let's go to our bonus. Our bonus is going to talk about the problem with queues. The problem with queues is it's easy to put objects on a queue, but it is expensive to remove them. And we're going to take a look at what that means right now. And this one is not nicely animated, so we are going to just go ahead and just drag and drop things by hand. All right, I assume everyone can still see this. Let me know if you can't. So putting items on the queue like the number 1, the number 2, the number 3, it's very easy. I can just drop them right on there. There's really nothing to do. The issue comes when I want to remove something like the number 1. Once I attempt to remove the number 1, I can remove it, but then I have to say, hey, number 2 goes down here, number 3 goes down here. You might think that they all move at the same time, but your computer can only move one thing at a time. All right. Very easy for my presentation, very easy for this beginner's example. But if you're dealing with a very large amount of data, we're talking about millions of things, you have to move a million things every time. It's very expensive. It can take a long time. Yes, the re-indexing takes a long time. And if I remove the number 2, I have to re-index again. I have to move each thing forward. And I have to do that every single time. There is a clever solution to this. I thought this was very clever the first time I saw it. And it sort of encapsulates problem solving in computer science. How do people solve these problems? A queue, we want queues. We need queues. How do we make them better? Here we go. And well, the answer is really not supposed to be there. Forgive me, it's a bonus. How do we make a stack into a queue? The answer is, well, flip it over. Flip the stack over. If you can just have the 1 be at the top of the queue, then, or at the top of the stack, now we can grab it out. That's the whole idea. All right, so let's look at what that looks like. Flip it over. We're going to take 2 stacks, and we're going to make a queue out of 2 stacks. Let me know if that makes sense to you. We're going to make a queue out of these 2 stacks. Here's what's going to happen. Just like before, the user has loaded up a stack. Excuse me. Let's actually make a name for this. We're going to call this a stack queue. Because it's a combination, so why not, right? I'm just going to put that on screen for my sanity. So the stack queue is now this object that we see here. It's a combination of 2 stacks, and it's going to behave just like a queue. So the user has put 1, 2, 3, 4, 5. In a normal stack, they can no longer receive that 1. They can't get to the 1. How am I going to get to the 1? See if you can describe that down in the chat. How am I going to get to the number 1, considering this is a stack? I just like to see it put in your own words. Flipping it entails, we are going to do something that is pretty slow, and it's very similar to reindexing. We're going to take each one of these items, so the number 5, the number 4, this is what we will consider for this, flipping the stack. Copy and reverse, I see in the chat. Yeah. So notice we didn't break any of the rules. This is a stack. I'm going to just show it one more time for effect. I'm removing the top item and putting it onto a different stack. I have not broke any rules about stacks. I can remove the top item and put it onto the other stack. And I can do that. Oops, how did I even do that? I can do that over and over until my in stack is now empty. So the user wanted to dequeue the number 1. And now I can say, hey, here's the number 1. There you go. Oops. Here's the number 1. And again, I still haven't broken any rules. Now maybe they want to put something onto our stack queue. Maybe they want to push the number 6 onto our stack queue. Sure, grab the number 6, put it on the in stack. Same thing, maybe you want to grab the number 7 and the number 8. We haven't broken any rules, guys. So far we got the number 1 out. They can continue to pop. Notice how this is, I'm not moving anything. I had to move things one time. I had to do the flipping. I can pop the number 3. It's instant. Awesome. I can pop the number 4. It is instant. And I can pop the number 5. It is instant. Okay, well, now maybe they want the next item. And I'm like, oh, wait, I ran out. They're not in order. I can't give you the number 8. That would break the rules. This wouldn't be a queue anymore. A stack queue. Well, this is time to now flip one more time. So go ahead and flip this 8, then 7, then 6. All right, that takes some time, but I don't have to do it every time. I have to do it sometimes. And now I can go ahead and give you 6 instantly. I can give you 7 instantly, and I can give you 8 instantly without having to do all that reshuffling for every item. I just have to shuffle sometimes. And that's the beauty of a stack queue. All right, and that's the end of my bonus section. I thought that was interesting the first time I learned it. And if you continue to look at data types and look at algorithms, you'll learn some interesting ways that developers have combined data types to make a faster or a more proficient program. All right, folks. So that's really all I have for you guys tonight. Thank you for the feedback in the chat. If there's any last things you want to add in or ask, you can go ahead and do those things. All right, and we're going to prep sleeve. Have to wait till flip the stack is empty. Is that flip task set by a parameter? Yeah, so David, we would just, let's go back a bit. Yeah, so we are checking when the user wants to grab something, we look at the out stack. If there's, in this case, there's a number 3 right there, just give them the number 3. Same thing, we give them the number 4 and the number 5. If you remember, one of the basic methods or one of the functionalities of a stack, that's to be able to know if it's empty. So when the user asks me for another item, I can very quickly check and say, oh, wait, my out stack is empty. When my out stack is empty, that's when I know it's time to flip. So that's how I'm going to know. If the out stack is empty, then I do the flipping. So 8, 7, and 6 will come out. And now I can start giving things to the user again. I can give them the 6, give them the 7, and give them the 8. Then the last thing, of course, if they try to grab something that's not there, I can check both stacks. And if both stacks are empty, I can tell the user, I have nothing to give you. Everything is empty. So I hope that answers that question. All right, Correct, David. It's only when it's empty. And that if we did it before it was empty, that would actually break the rules here. So let's just look at that really quick. If this is not empty and we attempt to flip it, that means the number 8 is now going to go on top. And look, now the numbers are out of order, and that breaks the rules of both a stack and a queue. So that would not be something that we want. Happy you enjoyed it, Justin. All right, folks. I will go ahead and sign off. Again, my name is Clarence Smith. Feel free to reach out to me on LinkedIn. Take a look at what I'm working on, or ask me more about stacks and queues. Totally open to that. You guys have a great night. We're going to go ahead and end the stream.